Welcome to the workshop. Today we want to take a look at alternating series and we want to determine the convergence or divergence of these two alternating series. The first example is pretty simple. Remember, if we want to determine the convergence or divergence, all we need to do is make sure that the positive portion of each term eventually goes to 0, as well as make sure, again, that positive portion of each term, right, ignoring the negative portion, make sure that this positive part is decreasing, eventually. So what we need to do in this case is first make sure that the positive portion of the terms actually goes goes to 0 as n goes to infinity. So the limit as n squared, or as n goes to infinity, of n squared over n squared plus 4. Now this is just polynomial divided by polynomial. So it's just the ratio of the leading coefficients when the degrees match, otherwise 0 when the degree of the denominator is higher, and infinity when the degree of the numerator is higher. In this case, matching degree tells us that it's just the ratio of the leading coefficients. So 1 over 1 is 1, which is not 0. So in this case, we don't satisfy the requirements to conclude that the alternating series converges, and we conclude that it diverges. The alternating series diverges. Excellent. So for our second example, we need to check the same things, that the positive portion of our terms, this portion, we need to make sure that actually goes to 0, and then we also need to make sure that it is eventually decreasing. All right. So we have the sum here we go. Limit as n goes to infinity of the natural log of n plus 1 divided by n plus 1. Now both the numerator and denominator go off to infinity, so we have a situation where we have an indeterminate form. That's what I'm looking for there. So what I want to utilize is L'Hopital's rule, so I'm going to indicate that by LH, L'Hopital's rule. So the derivative of the numerator would be 1 over n plus 1, and the derivative of the denominator is just 1. So overall, we're just left with the limit as n goes to infinity of 1 over n plus 1, which is in fact 0. So we satisfy the first part of showing that the alternating series converges. Excellent. Now the next part is we need to show that this thing is also eventually decreasing. And in order to do that, there's a couple of different approaches that we could take. The first approach would be to simply consider the graphs of the two functions and observe what happens. So natural log of n plus 1, essentially, maybe a little bit off, not too big of a deal, and the linear function. So whether this is exactly right or not, this portion here could maybe look a little bit different than it actually does, but the main focus is that the linear function continues to go upwards at a constant slope, and the natural log function, the slope eventually goes towards 0, so we're going to have that this continues to surpass, and so the numerator is continuing to get larger at a faster rate than the natural log function, so we can be confident that the terms are going to continue decreasing in absolute value. So that would be sufficient, but we could also consider f of x given by natural log of x plus 1 divided by x plus 1. then the derivative, of course you have to use the quotient rule in this case. So the derivative is given by x plus 1 minus x times the natural log of x plus 1 divided by x times x plus 1 squared. In order for this to be larger than that, let's see here, x plus 1 minus x times the natural log. Oh, yes, excellent. So we want this to be larger than that, right? We want it to be negative overall. So, and that certainly happens. Where exactly it happens, I don't know, but x times the natural log of x plus 1 is certainly eventually larger than x plus 1. So larger than 0 eventually. So hence, or thus, whatever transition word you would like there, thus f of n plus 1 is less than f of n eventually. But that is, this gives us exactly the a sub n plus 1 is less than a sub n, or more explicitly in the context of our problem, natural log of n plus 2 divided by n plus 2 is less than the natural log of n plus 1 divided by n plus 1 eventually. So this allows us to conclude that we satisfy the second condition for the convergence of an alternating series, and we say, therefore, the alternating series, sum from 1 to infinity of negative 1 to the n natural log of n plus 1 divided by n plus 1 converges. So again, in the first case, we had a series, an alternating series, which did not satisfy that the positive version of the terms goes to 0. So if you were worried about what exactly the justification is that it doesn't converge, this would simply be a variation of the nth term test. If you included the negatives here, it's just bouncing between positive and negative 1, or it's approaching positive and negative 1. So we would have that the limit does not exist. Still, that's not 0, so no convergence. Here, we have that the limit of the terms is, in fact, going to 0, and then we were able to justify either graphically or using a derivative to show that these terms are decreasing. They eventually get smaller, and then from those two facts, we can conclude that the alternating series does converge. Excellent. Thank you for joining me in the workshop today. I hope to see you guys again soon, where we talk about absolute and conditional convergence. I'll see you guys soon.